So now we're going to talk about a topic in section 1.6, or the topic about section 1.6, which has to do with function inverses. So first we're going to talk about invertible functions, what they are. The inverse, quite simply, is, undoing something. So if you think about a function, f of x plus f of x equals, let's say, something nice and easy, x plus 2, then we're looking for something that does the inverse. So as you know, the inverse simply means something that undoes. So what would undo, doing f of x, taking the independent variable and adding 2? Well, it's pretty easy just by inspection. That would be taking and subtracting 2. Now to keep these things differentiated, that is, how we can tell them apart, we use the inverse. As in, we say f inverse, that's what this -1 power means. If you think about it, the multiplicative inverse is taking the reciprocal, right? So if I take 2, the multiplicative inverse of 2 is 1/2, which is the same as saying 2 to the -1. That's why we use that for inverse. So this piece here, this right here, means that we're looking at the inverse. Now, the idea is that the inverse undoes what the original function does. So let's take a look. If we compose these, that is, if we do one and then the other. So let's say that we do f of x, and then we do the inverse to it. What should happen? Well, without guessing, we know that the inverse is, the original function is x plus 2, right? And we're plugging that in to here, and then we do minus 2. So what happens? X plus 2 minus 2 is x. In other words, we're taking and putting in this value, this independent variable, some value x, and we're doing something to it, and then we're undoing it. And then what happens? We get the original thing back. It's like we kind of chased our tail and caught it. Now, this is an inverse function, however, so f inverse needs to be a function. So this leads us to some interesting stuff. Let's take a look at a couple more things. So when you're looking at an inverse, if you're looking at x and then f of x, right, then what happens is, let's say it's 1, 2, 3, 4. Let's say that this is 4, 5, 6, 7, right? Then that would mean that the inverse would take, well, it would have a new independent variable, which is technically f of x, and it would have a new output, which would be f inverse of x, right? And this may seem confusing, but it means 4, 5, 6, 7 would go in, and 1, 2, 3, 4 would come out. Okay, watch this. X, we normally think of this as the y, right? Which means that this is the y, right? F of x is y, that's the y. And x, well, these are all the x values, so guess what f inverse could be thought of as, right? So what we've got as a transformation is taking xy values, and it is making them into yx. Now if this looks familiar from geometry, which maybe it does, maybe it doesn't, this is a reflection over the line y equals x. So it turns out that the inverse also has a graphical representation. Now, that's very compelling and very powerful, but it has some drawbacks. To wit, if I were to take a look, and if we think of the inverse, so inverse as a, oops, let's go ahead and boldly not make this in one word, a reflection over y equals x. Now if you don't remember what that looks like, it's actually not that bad. So xy, right? Plane. The line y equals x is this linear equation here, right? Let's touch that up a little bit, okay, so it's actually, right? So that's the line y equals x, and y equals x. So if I were to take something, so let's say I've got a function f of x. You guessed it. Now, I'm picking this for a reason, right? So that's my function f of x. If I were to reflect it, that is, x becomes y, y becomes x, then that means I'm reflecting over the line y equals x. And it turns out, now this is not necessarily entirely accurate how I've drawn this, but what would happen is that all these values would be equidistant from on the opposite side of the line. So this point would map over here, this point would be down here, and so on. And if you kind of keep that going, points that appear to be on the line would be, so you end up with a curve that looks kind of like this. In this case, it's kind of like we've reflected this quadratic, so this would be my f inverse. Now, it's important that the inverse must be a function. And remember, a function passes the vertical line test, right? Which means passes vertical line test, aka 1y for each x. So if you look at this, this fails miserably. Meaning, if I were to take a different color, let's say I get those vertical lines, see how vertical I can go here. That's about vertical. And I were to pass this to the original function, all well and good. See, it's only hitting once for the green function. When you get to the blue function, it fails pretty much immediately. So what does this mean? It turns out that this isn't the inverse, and it turns out that this function isn't even invertible. Okay, so let's take a look at this. What makes that function not invertible? So let's try this on. So we were looking at something that looked suspiciously like y equals x squared, right? Something like that. What characteristic made this not? Well, if you were to pass a horizontal line through this particular function, what do you notice? It hits twice, which means that for this given y value, it's got two x values. So it turns out, in order to be invertible, I'm going to type this so you can actually read it. In order to be invertible, a function must be 1 to 1. That is, there must be only one x value for every y value. Functions that are invertible are said to be 1 to 1 functions. So you can have a function that's still a function, but it might be not be a one-to-one function, and a quadratic is an example of that. Okay, kind of some key elements here are the whole one-to-one thing, and indeed the horizontal line test is the key way. So doing this, you can actually figure out if something's invertible right off. So for instance, if you were looking at a function that looks like this, mark 1 mod 0 cubic, all you do is you draw up your horizontal line, or you can just visualize it, and this fails miserably, right? Not invertible. Now, it turns, oh, there's an L in there. See, that's an L? Okay, that's a mess. It turns out, though, that you can make functions invertible by restricting what you're looking at. So let's just say, for argument's sake, I were to cut this function like right here, like that vertex, right? And I was just to look at that piece of that function. Well, if I was to do that, then I'd be looking at, well, whatever that x value is, but I'd be just looking at still just a function that looks like that. I'd be just looking at a piece of it, right? So that's still this function. Let's call this f of x, right? what's the difference? Here I'm looking at f of x, but I'm only looking at this x value, let's call that x at 1, and greater. So we'd say that x is greater than x sub 1. That is, we're just looking at this piece. What we've done is we've restricted the domain. So this is a domain restriction that makes the function that makes the function invertible. And we'll talk about actually how you find the inverse in the next video.